One of the trickiest things about traveling through the vast vacuum of interstellar space is that it isn't a vacuum. So today we are going to be taking a look at some of the difficulties involved in interstellar spaceflight and some features of spaceships we haven't discussed before for time constraints. We have looked at spaceships many times, and interstellar colonization too, but today's topics take some time and were never absolutely vital to the topic at hand. Here are the key topics we will be covering today. Number 1. How fast ships can go. Number 2. The non-vacuum of space. Number 3. Collisions and protection. And number 4. The shape of a ship. We will also be rejoining our Gardner ship, Unity, from the Life in a Space Colony trilogy. You don't need to have seen those episodes to follow along with the discussion today, but it saves some time to use them, and I've grown rather partial to the ship. As a reminder, that ship, massed in at a couple 100 million tons, was half a kilometer wide and a few kilometers long. We have visually rendered it before, but that was always more conceptual than accurate. It had a crew of 200,000 when it left Earth for the Tau Ceti system, and as it traveled at 10% of light speed, it needed 120 years to arrive there. They had a lot of people born during the trip, and also enjoyed massively extended lifespans, something we'll discuss more next week. Plus, they were receiving constant, if delayed, tech updates from Earth, and you can make a lot of technological progress in a century. All of which meant they had more people when they arrived than originally planned, and the technology to do the job better and with less people. Many of the folks had adjusted to thinking of the ship as home, and been raised to think of colonizing solar systems as their life purpose, and their worldview probably would have altered to view that as one of the greatest accomplishments a person could labor towards. So it was no big surprise they decided to continue their journey onward, planting colonies like seeds in a great big galactic garden on an eternal journey toward the edge of the galaxy and maybe beyond. But the ship was not designed for that, and again they've got a century of technological progress since the ship was built, so they decide to retrofit Unity before leaving Tau Ceti. They pick as their next destination 82G Eridani, a system around a yellow sun that, like Tau Ceti, is a bit older, smaller, and dimmer than our own sun. It is more or less in the same direction Tau Ceti is from Earth, just a bit further along. Tau Ceti is 12 light-years from Earth, and 82G Eridani is 20, but it's about 12 light-years from Tau Ceti, being off at a bit of an angle. So it will take them as long to get there as their first trip. They'd like to do it faster, and not need 120 years to cover 12 light-years. The engineers say they can boost the speed to 20% of light speed and a 60-year journey. However, they are leaving with just a bit over 50,000 people, so they still need to repopulate. But you don't need a century to double or quadruple your population, especially when folks are not aging. They don't die off and they can keep having kids indefinitely. So they have no problem rapidly increasing their numbers in a few generations. Though generation ceases to mean anything in this context. People are still having kids while their grandchildren are. They're thinking they need a larger ship too, not just a faster one. So we need to retool the ship, and the captain calls a meeting of all the senior staff, ignoring for the moment that we have been assuming this was a democratically operated civilian vessel who probably has an elected provisional governor calling such shots. Same captain as before. She looks mid-20s but has been commanding ships since the old interplanetary vessel Hyperion, so there's a couple centuries of experience there, and her actual rank or rating is probably something like Grand Admiral by now, and she runs a ship that has more people in it than most top-tier navies have personnel. How fast can we go, she asks, and why can we go faster now? Her science officer speaks up and says that's not how this sort of thing works. We can go as fast as we want. The problem is it takes exponentially more fuel to go faster. Every type of fuel that classifies as a rocket has an exhaust velocity, how fast the stuff comes out the back. To get your ship up to that speed, you need for 63% of it to be fuel. That's just how it is. And if you want to be able to slow down at the end, you need it to be 86% fuel. A ship that doesn't need to slow down can get twice as fast as one with the same fuel ratio, if you're curious. If you want to get to double your exhaust velocity and not slow down, you need to be 86% fuel. If you want to slow down, you need to be 98% fuel, leaving only 2% of your mass for ship and cargo. If you want to get to triple that speed and slow down, you need to be 99.75% fuel, meaning you've got 400 times as much fuel as your ship and its cargo. This is why we need rockets the size of tall buildings to get ships the size of cramped apartments into space from Earth, because the exhaust velocity of a normal rocket fuel is considerably less than the escape velocity of Earth, even ignoring air drag. Getting to higher and higher speeds compared to your rocket exhaust velocity requires exponentially more fuel. Their ship, Unity, used fusion, which has vastly higher exhaust velocities than chemical fuels, usually estimated at a decent if low percentage of light speed. The science officer says that what changed is the new reactor designs from Earth let them achieve a more efficient degree of fusion and results in a higher exhaust velocity, twice what it was before. We'll say it used to be 5% of light speed that the fusion products and leftovers flew out at before, and now it's 10%. That's on the conservative lower and higher end of what we anticipate from a good fusion drive. It also means that whatever the mass of the ship and the cargo is, when fueled up, it will be about 50 times more massive than that, and when it is done accelerating after some weeks or months to its cruising speed, it will still be about 6 times more fuel than ship. The captain asks why not just go with a higher ratio, even more fuel. After all, there is no shortage of hydrogen available, nor minerals to make the tanks out of. But that's where the weapons officer chimes in. It won't work, he says. The current system was designed to let them avoid collisions in interstellar space at 10% of light speed. By going twice as fast, they will encounter those objects twice as often, and each carrying 4 times the energy and damage capacity. The science officer nods and picks that up, as he's a bit of a long-winded fellow who usually needs 20 to 40 minutes to get to the point. He says the interstellar medium, all the gas and dust between the stars, is quite thin, and most of it is hydrogen and helium gas molecules, with the supermajority of the tiny amount remaining being very tiny motes of dust containing a handful of atoms too. Those are not a problem, they act like radiation, and you just make your forward shielding a bit thicker. Ours will mostly be thin metal containers full of fuel, hydrogen, because hydrogen is quite good at stopping radiation. What we have to worry about is things that will make big holes, or even trash the ship. And since smaller particles are a lot more common than bigger ones, we will run into a lot more of them. As a very loose rule, when it comes to meteoroids and micrometeoroids, there's about an inverse relationship between mass and frequency. You expect to encounter stuff twice as massive about half as often, meaning that since everything is hitting us with 4 times the energy, since we're going twice as fast, something with a quarter of the mass will do the same damage as when we're going half the speed. But those objects are now 4 times as frequent. To make it worse, since we need to vaporize this stuff and are going twice as fast, we will be encountering them twice as often, so 8 times the frequency of the stuff we need to shoot down, and we need to detect them twice as far out to have time to react to them. We need to detect smaller things further away. Even worse, our little local bubble of the galaxy is rather low in density compared to the galactic normal, which is about 10 times thicker than the interstellar medium is locally. This ship is not going to remain in that bubble, and indeed may pass into areas where the density is far higher, so best prepare now while we are making our ship bigger, faster, and better. Nor is the medium homogeneous. You might go through short patches where the density is hundreds of times higher. Needless to say, this all gets worse the faster we get. At the speed we are going, your typical grain of sand, weighing about 1 milligram, would hit us like half a ton of dynamite, or around 1,000,000 times the energy of the average bullet. We can easily armor the hull against normal bullets, but these are pinhead-sized objects that will penetrate rather deeply, leaving small, long holes. So even one just carrying that much energy is something I'd rather not be hit by. Even as huge a target as Unity is, being half a kilometer wide and tall, we still will only encounter about the equivalent of a bucket of sand during a century-long trip, in terms of cosmic dust, and most of that will still be too small to hurt us even at these speeds, but it is still enough that you might expect to run into a grain of sand as often as once an hour, and something the size of a pea, which would hit us like a small nuke, maybe once a month. But something carrying bullet force? That we would run into almost every second, and it would be only a handful of micrometers across, the width of the thinnest hairs. We need to see that tiny mote far enough out to target it with a laser and vaporize it, and we are traveling 60,000 kilometers a second, fast enough to travel from Earth to the Moon in 6 seconds, fast enough to get to the Sun in 40 minutes. Even computers need time to get an accurate track on an object and aim, which usually involves moving something, then shoot and hit something smaller than a grain of sand, though we'd probably use a wide beam and go for overkill to compensate for positional uncertainties. Needless to say, it takes a very powerful radar system to get returns off something that small far enough away to help us. And it can't be classic radar either, using radio waves, because you cannot detect and track something smaller than the wavelength of light you are sending at it. When you listen to an FM radio channel, those waves are about 3 meters long, so a radar using them would have problems seeing and tracking something the size of a person. Even millimeter radar isn't good enough for us. Not even microwaves are. We need infrared. Most types of dust and sand also absorb infrared, often reflecting only a few % of most wavelengths, giving us weak returns on our radar. Handily, many are very reflective of about 1 to 3 micrometer wavelengths, which in this case is what we need. So a weapons officer shakes his head and says, "Look, Captain, I think we can buff up our current system to handle this, but I can't make a lot of guarantees. Maybe we ought to just stick to the same speed and be happy we can carry a lot more cargo on a lot less fuel than before." But fuel is cheap. She doesn't really care how much we use. Any of a million small comets hanging around a solar system will have plenty of hydrogen, even without needing to try diving into gas giants to get fuel. So if there is any chance of safely shortening the trips, she wants to take them. So she asks the science officer if there are any options. Plenty, he says, but none of them are pretty. The captain says she doesn't care if they take a lot of time to add on and maintain, and he says no sir, he's being literal. Most of the options just don't conform to a nice-looking, streamlined ship from ancient science fiction. She reminds him that they weren't planning to enter the ship in a beauty pageant, and since they are going where no man has gone before, it is unlikely we'd encounter any anyway, and to get on with it. So the first option is thicker armor. When we're done expanding the ship, its dry weight, its weight minus the fuel for speeding up and slowing down, is going to be around 1 billion tons of ship and cargo. The front cross-section of the ship is about 200,000 square meters, so if we're making our armor out of a big meter-wide metal-shelled cubes full of hydrogen weighing a ton apiece, that would only be 200,000 tons out of 1 billion. Doing those 5 layers thick would only be 1 million tons. Tiny holes a few micrometers thick through a centimeter of metal won't leak gas fast. But over a century those would empty out easily, and it's awkward to patch and repair that area with all the radiation in micrometers. Doable but kind of rough. So we could set it up like a conveyor belt. The front isn't a big sheet anymore, it's the ends of thousands of little conveyor belts, where the belt is made up of metal cubes full of hydrogen. They rotate out and back in again, and at the backside they get repaired. And the belt widens out at the front to provide a few layers of overlapping armor, and we slide a new section forward whenever one takes an impact. Let the robots do the repairs in the rear, and keep some spares on hand. It hardly needs to be airtight, just packed close enough that almost nothing can slip through, and we'll have another layer of more normal armor behind that. In fact, we'll store most of the fuel up front, with habitation sections behind them. If a big collision happens, and you need to replace a big chunk of the assembly though, we have another option. We can shoot a small solar sail ahead of us, itself just a micrometer thick. Just launch it and have it unfurl and act as a temporary shield. Most stuff hitting it is going to slam right through, but fragment a lot or be deflected to the side just enough. It would act a bit like an umbrella. It would slowly drift back into the ship from collisions, and you could grab it then and drag it back inside and recycle it. Just a tinfoil thick shield. Even if we couldn't recover it, the total loss of mass would be just a few tons out of 1 billion. The captain asks why we can't make that foil shield thicker, and the science officer shrugs and says we can, but we would be better off having several of them ahead of us, spaced way out in front, not meters or kilometers, but whole light seconds ahead of us. She points out that the front one will just be shoved back into the next one, and so on, until they get slammed into the front of the ship. The weapons officer points out they will also get in the way of the ship's radar and lasers, so it won't work. But the science officer shakes his head. We will place them far enough ahead that the last one is just outside our minimum engagement distance, say a tenth of a second, more than enough time for the ship to still locate, target, and fire on something that makes it through. But it doesn't matter, because we will keep the shades strung out at the right distance by pushing on them with our own lasers, just using them defocused. They are a solar sail after all. And we will put sensor packages on them too, adding a little weight but not much, and we can power those by having a few solar panels we will target diffuse lasers on. When they get scrapped, we will give them a little side shove and let them drift back to us on the side and just snag it and drag it in for recycling and repair. We are going to put a lot of our lasers off to the side of the ship, extending on big, long, thin telescoping antennas to keep them rigidly locked to the ship and to provide power and data flow back to the ship. At the end of those will be a big laser and radar, giving us better detection and an angle to shoot at, also letting us more easily push things to a side. Those telescoping antennae or arms won't be very massive. You have a dozen or so of them telescoping out several kilometers to the side, radiating out like the spokes on a wheel. If one gets damaged, and they might because they won't be much shielded, you just reel it back to the ship and repair it. Even if one gets snapped off, it won't drift much or fast, and you can shoot a grapple off to snatch it and reel it back in and repair it. We can also shoot probes ahead of us, either with their own fuel supply or pushed and powered by lasers, just expendable things to detect stuff ahead of us, and maybe even some weapons of their own. Even if they each weighed several hundred tons, we can deploy them on a regular basis. Indeed, if we can microsize our fusion drives enough, we might want to send Mini out ahead of us to slow down and park on some comet along the way to act as a fuel supply for a big radar and signal relay, maybe even with lasers to help clear our path for us, or just have them keep going and do a flyby of our path and destination. We've talked about using laser highways as an ultra-cheap and fast way of traveling between existing colonized systems, and there's a lot to be said about laying that down on the original trip. This would be a good way to get started if we wanted to, and had drives small enough. The head of maintenance complains they'll be constantly having to fix, build, and repair stuff, but the captain shrugs and points out they are essentially a massive factory ship, and always have to anyway. Truth be told, this would seem to require very little personnel. She says, alright, let's do it. And the science officer asks which system, and she says, all of them. They wouldn't seem to interfere with each other or need much mass or energy to operate. And they'll go ahead and scale the ship up too. But only in length. No point adding more cross-section to armor and defend. A ship twice as long doesn't need twice as much frontal armor if you're just making it twice as long, not twice as wide. And that means the same amount of armor still guards twice as much ship. This is a key reason why when we discuss interstellar ships on this channel, I so often treat them as objects more akin to flying city-states than a classic small cruise ship of a cast of half a dozen, or even big ones like on Star Trek with a crew of hundreds. We look at ships that are thousands of times more massive than modern battleships or aircraft carriers crewed by hundreds of thousands, if not millions, not because they need that much crew. They don't. The ships would probably mostly run themselves and just need a couple dozen people to make decisions and handle unexpected events. Even then, only if the ship didn't have human-level artificial intelligences on them, when in all likelihood they would, or something smarter. The same kind of automation that lets you have ships that only need small crews, or none at all, to operate for decades, trillions of kilometers from home, is the kind of automation that lets you build leviathans like we look at quite cheaply. The problem with smaller ships, especially tiny probes, are manifold, and I discussed those more in the space warfare episode, but there they had the advantage of being hard to intentionally hit. But we are not expecting to be shot at, and by scaling up in size, we benefit in a lot more ways. The small ships need just as much radar, just as many lasers, and so on. They also need some sort of power supply, And the fact of the matter is that even if you could make a fusion reactor very small so it would fit in a car, it is just the nature of such devices to be more efficient when larger. There's only a few realistic options for going faster than fusion. We've discussed them before, and they pretty much all require using photons or maybe neutrinos as your rocket exhaust, if you have exhaust. One is laser push ships, where being bigger does help since your aft mirrors for getting pushed on can be bigger, allowing more distance for those pushing lasers to target you. These let you get very fast since the rocket equation doesn't apply, no fuel, but have the issue of slowing down, requiring either slowdown fuel or something like the interstellar laser highway we discussed in the interstellar colonization episode back in year 1. Another option is black hole starships, which we gave a whole episode over to, and those had to be massive ships just by their very nature, as we discussed there. The only serious option for a faster ship than fusion can give you, while being smaller than an aircraft carrier and being able to slow down, is antimatter. The main byproduct of combining matter and antimatter is photons, which obviously have an exhaust velocity of the speed of light. That doesn't mean you only need an amount of it as implied by the rocket equation to get near light speed though. We worked with speeds today and in the past where we could almost entirely ignore special relativity. At 10% of light speed, you are getting a gamma of just 0.5%. A meter-long object is half a centimeter shorter. Your clocks are running slow by about 1 second every 3 minutes, or about 7 minutes a day, and an object needs just a little more energy to get to that speed than classic Newtonian equations say. At 20%, those effects have jumped up to about 2%. A meter is 2 centimeters shorter. Clocks lose about a second a minute relative to Earth normal, so a 50-year trip on Earth's calendar only took you 49, and there's a small but noticeable increase in energy over Newton. Even at 50% of light speed, these effects aren't too huge yet, they jump to 15%. At 86% of light speed, they double. Even your light speed exhaust velocity is straining to get you any faster, and beginning to need huge ratios of fuel to ship and cargo, and every object you hit whacks into you with an energy of its mass in antimatter. At 94% it's tripled, and 97% quadrupled, quintupled at 98%, 7 times higher at 99%, 10 at 99.5%, and it keeps getting worse. Now at those speeds, space really does have enough drag that you want to be thinking about aerodynamic shapes too. And nothing could push a ship this fast as an onboard fuel you carried, not even antimatter at fuel mass ratios of thousands to 1, and you'll need to constantly add in more energy just to maintain this speed against that drag from space gas. And all but the tiniest motes of dust need to be vaporized so they don't smash your ship like a nuke. You'd probably need to punch those molecules with a laser so hard they ionized, so a magnetic field around the ship might shove them aside. And that would need to be one heck of a magnetic field. And yes, most ships probably would have big magnetic fields, because they will provide a little protection from anything carrying an electric charge, and a decent fraction of the stuff in interstellar space is ionized, or will be when you're zapping them with lasers, especially if those are in the ultraviolet or X-ray range of the spectrum. It won't help with collisions, but it will decrease the ambient radiation from all the stuff too small to shoot. It's why I don't ponder faster than light travel much. Beyond its dubious nature as what is basically a mathematical gimmick, it's not like even getting near light speed is a real option, because it requires obscene expenditures of energy compared to just going half as fast. And there are other things you can do with that energy which are better alternatives than trying to get there a bit faster and having to employ the kinds of radar systems that would glow like miniature suns and need massive supercomputers just to track everything so you aren't annihilated by a random grain of sand. Those collisions and radiation begin becoming the real problem, and no cool space drive is going to magically make those go away. Your best bet for real interstellar travel to places you've already been is to have a long chain of fusion-powered laser relays, shoving ships around and constantly tracking everything in their corridor to keep it free of dangerously large space dust. Again, that laser highway. Even then, especially since those ships need large sails for targeting with lasers, I wouldn't ever aim for more than 86% of light speed. Same for antimatter. It just isn't worth going faster even if you can produce the substance for peanuts and store it safely. Frankly, both are kind of silly speeds anyway. You don't engage in routine interstellar travel unless you have either biological immortality or can freeze and thaw people, and as I've discussed before, the latter ability almost requires the former. In which case time doesn't matter much. Everything still takes many years that your destination experiences, and you either don't or don't care about it because you've got as much time as you want. That's our topic for next week, life extension, something we looked at briefly last year but we'll look at in more detail. So on ship speeds, for fusion, depending on how good it gets, anywhere from 5 to 30% of light speed, though the latter is really pushing it unless you've got some material that can reflect neutrinos. Micro black holes can do better, especially if you can feed them, ditto antimatter and laser sails, but realistically not much over half to maybe 90% of light speed. As to shape, your typical interstellar ship ought to look like an unsharpened pencil, and as we discussed before, the energy needs to get up to just a tiny fraction of light speed so dwarf the energy needed to operate life support and operations that even on a wasteful glutton's budget over centuries, they would look like a rounding error compared to your fuel needs. Our lasers and massively overpowered mega radar will add to that, but not too much. Yet while the main body of the ship might look like a pencil, it will probably have those frontal foil shields stretching over millions of kilometers ahead, and thin projections sticking out to the side like spokes on a wheel, another reason why the outer hull of the ship either does not spin or does so very slowly, even though you'd have big rotating habitat sections inside. 250 meter radius is probably as wide as you'd ever build a ship, since that is our estimate for the widest you'd need to maintain Earth-like pseudogravity that people didn't get motion sickness from. Hopefully by now, you've got a pretty good idea why these sorts of ships never have maximum speeds put on them, or almost always get described as very long and narrow. Totally different ballgame from interplanetary ships, though they'd also probably be long cylinders with a big forward shield telescoped out ahead of it and spoke-like projections for sensors and collision lasers, just scaled down a lot. Spaceship designs are never going to look very cool, or maybe we'd change our notion of cool. After all, planes and sports cars and motorcycles and rockets are not objectively that cool looking, but we've come to view them that way for all the implied speed and power of the design. Okay, we'll stop there for today. Next week we will look at life extension in some more detail, and look at how that might actually happen in our lifetimes, along with some of the implications of that on society. We've discussed it before in bits and pieces, but this time we'll focus down more on the technology, the hurdles and challenges, and the impacts of it on civilization. Make sure to subscribe to the channel for alerts when that and other episodes come out. And if you enjoyed this episode, please like it and share it with others. Until next time, thanks for watching, and have a great week.